Welcome to this explainer, based on the teachings of Deshmukh Sir. Today, we're diving straight into the fascinating biology of exactly why we look the way we do. If you've ever wondered why you might share a nose with your grandfather but have completely different hair than your siblings, well, you're in the perfect place. We're talking heredity, variation, and a surprisingly quirky physical trait that maps it all out for us. Section 1. The Earlobe Enigma, a physical mystery. Let's start with a quick, hands-on experiment right where you're sitting. Seriously, reach up and feel the lowest part of your ear right now. Just give it a little tug. What does it feel like? Specifically, is that little piece of fleshy tissue at the bottom dangling freely, or does it connect in a straight, continuous line right into the side of your head? As you'll see, human populations consistently feature two very distinct variants here. On the left, we've got free earlobes, where that lowest part just hangs freely. And on the right, attached earlobes, where the tissue connects closely to the side of the head. It's a binary physical trait, plain as day. But making this simple observation actually sparks a much bigger, much more profound mystery. Why do these specific physical variations even exist in us? Like, why aren't human ears all built the exact same way? It turns out this tiny little difference on the side of our heads opens up a massive door to understanding how human bodies are designed and built across generations. Which brings us to Section 2, the basic human blueprint, similarities and differences. Deshmukh Sir points out a really foundational truth here, stating that the most obvious result of reproduction is the production of individuals having a similar basic design. Basically, when humans reproduce, the offspring are invariably human. The underlying blueprint, it's incredibly reliable. But here's the paradox of that blueprint. A child absolutely has all the basic features of a human being, sure, but they are never an exact carbon copy of their parents. Because of this, human populations show just a massive amount of variation. We share the overarching design, but the specific details, like that earlobe you just tugged on, well, they vary wildly. Moving on to Section 3, defining heredity and traits, passing down the code. So think of heredity as the bridge between generations. It's the formal biological process through which traits and characteristics are reliably passed down from parents to offspring. It's exactly what maintains our similar basic design while simultaneously serving as the vehicle for our individual differences. And crucially, heredity isn't just some random game of chance. There are hidden, highly structured rules that determine exactly how physical traits make the jump from parent to child. Your earlobes didn't just wake up and decide to be attached or free out of nowhere, right? They followed a strict biological code passed down from the people who made you. All right, Section 4, the classroom experiment, Activity 8.1, Earlobes. To really grasp this, Deshmukh Sir outlines a brilliant hands-on classroom detective mission known as Activity 8.1. The first phase requires us to play detective and gather real data. Step 1, observe the ears of everyone in your classroom. Step 2, prepare a list categorizing every single student as having either free or attached earlobes. And Step 3, calculate the percentage of each type. It's a super simple data collection exercise, but it immediately grounds these abstract biological concepts right in the real world. If you actually run this exercise, it generates concrete data, allowing us to calculate the exact percentages of each variant. You might find one trait vastly more common than the other, or maybe it's a perfectly even split. Visualizing this data reveals the sheer scale of physical variation sitting right in front of us every single day. But hey, gathering classroom data is only half the job. To truly understand inheritance, Activity 8.1 instructs us to trace the trait backwards. First, you find out the earlobe type of the student's parents. Then, you compare the student's earlobe directly with their mother and father, essentially mapping the trait from one generation to the next. By doing this, we connect the generations to reveal the hidden patterns at play. For instance, you might find a student with attached earlobes actually has two parents with free earlobes. Or maybe a student with free earlobes has parents who both have attached ones. By mapping these specific similarities and differences across generations on a large scale, the abstract rules of heredity suddenly become visible. We literally get to see heredity in action. And that leads us to Deshmukh Sir's ultimate, provocative challenge to you. If you were the one observing all this classroom data, tracking the family histories, and mapping the earlobe variants across generations, based on those observations, what possible rule for inheritance would you suggest? What do you think is the hidden code deciding the shape of your ear? I want you to really think about that the next time you look in the mirror. Thanks for joining me for this explainer, and keep observing the fascinating variations in the world around you.